My name is Princess Ba and I'm from Chadron State College, and my research was on the qualitative and quantitative analysis and determination of menthol in peppermint tea. This is the structure of menthol and its isomers and stereoisomers. A little background on peppermint. Peppermint is one of the main species of mint. There are two main species, peppermint and spearmint. I decided to go with peppermint because it has a higher percentage of mint than spearmint, and it's also one of the most widely consumed herbal teas, hence it's in high demand. A bit on menthol. Menthol is a major component of peppermint, and it has antioxidative properties which stabilizes compounds and prevents oxidation. Menthol also has its natural aromatic decongestant, which helps break down phlegm and mucus and helps to expel mucus easily when a person has cold. Menthol also has a cooling effect, which helps in relieving sore throats, especially when it's used in tea. Menthol also has pharmaceutical properties in humans, which helps in the enhancement of lungs and airway volume, which also helps when a person has cold. The purpose of this research was to find the consistency in concentration levels of menthol in peppermint tea, and this is because as a result of the high demand of peppermint tea, there's a tendency to use low-grade raw materials rather than the menthol, which is supposed to be used in production. The hypothesis of this research was that there will be changes in the menthol concentration levels between different brands of peppermint tea, but there will be little to no changes between peppermint tea in the same lot. The methods I used, I measured the tea with menthol spikes in order to see changes in the peak sizes. I brew the tea first, and then I extract it, I filter, and then I inject. And then I run it through the HPLC column and determine the peak levels. I filter the tea because after extraction and brewing, there are sediments that settle in the bottom of the beaker. And if these go through the HPLC column, it will contaminate the column and affect the results that I get out. So I brew 2 bags of tea for each run I do, 2 bags of tea in 125 milliliters of water, and then I allow the tea to steep for 5 minutes, and then I cool it before extracting and filtering and then injecting into the HPLC column. These are the materials I use, and these are the 2 brands of tea I use. I use Great Value and Bigelow tea. I use 2 different lots of Great Value and 2 different lots of Bigelow tea, and then I made my comparison between the 2 brands also. This is the HPLC machine, and there are 2 pumps in the HPLC machine. I ran a gradient for my research, and I used these 2 pumps, and then I used acetonitrile and a 50-50 methanol water solution as my solvent. The first pump, I set it at 0.0, and then the second one, I set it at 0.5. And as I ran the gradient, I adjusted the time and also the concentration levels on the pumps. So for the first 3 minutes, the first pump ran at 0.0 and the second one ran at 0.5. And after 3 minutes, I switched the pumps, and the first pump ran at 0.1 and the second ran at 0.4. I did that throughout the time frame of 25 minutes for each run. I started with pure tea first, so I injected the tea into the HPLC column, and I determined the peaks that came off on the computer. And then I figured out what the illusion time was, and I recorded the data. And then after I did the pure tea, I did the spiked ones too. So I injected 0.125 milliliters of pure menthol into the 10 milliliters of pure tea, and then I injected those into the HPLC column. And looked out for an increase in the peak area on the computer. For the purity, I got similar graphs for the lot 1 and lot 2. The first lot came off about 0.23, and the second one was close to 0.5, so about 0.245-ish. But both graphs have similar peaks and come off at the same points. Their illusion times are similar. And then when spiked, there's an increase in the area of the illusion time. So I used a particular math formula to find the difference in the areas between the pure T and the spiked T. And I recorded the data and made the comparison. This graph kind of looks off, but when we look at the time in which they can come off, it's similar to the first lot, and the time it's similar to the first plot, and the peak sizes also increase between the pure T and the spiked one. This is the second brand, the Bigelow Pure T. The time it comes off, the illusion time, is also similar in both lots, and the peaks are similar, and the observance levels of the peaks are also similar. When compared to the spiked T also, we find similarities in both of them. Also, there's an increase in the peak levels in both of them. These values show my concentration levels of menthol that are in the pure T samples. For the calculation, there was a certain amount of menthol that was used to spike each of the T, and it had a constant value. But to determine the area of the amount of menthol in just the pure T, we had to do an algebraic calculation to find the values. And to see the averages between the gray value lots and the Bigelow lots are kind of similar, and they are all in the same range. But when we look at the p-values, we're able to make a perfect determination on the comparison between the lots and the brands. And our p-values for the two gray value T lots was 0.7099, and for the Bigelow T it was 0.0261. And when we compare the two brands, the p-value was 0.6947. And these values, when compared with our alpha value of 0.025, they support the hypothesis that says there are going to be changes between brands, but similarities between lots, because the values are higher than our alpha value, and so we fail to reject our hypothesis. In conclusion, the peak of the pure samples of menthol are similar to the spikes that are seen when both menthol and T are run through the HPLC column, and then changes occur in the peaks in the different brands and lots. And we accept our hypothesis between the lots and also between the brands, because when we compare our p-values to the alpha value of 0.025, we fail to reject our hypothesis. For future research, I would like to look into how menthol levels in the body affect oxidation of compounds, and also how the interaction of menthol goes with active ingredients in peppermint tea. I'd like to thank Chadron State College for allowing me to use their equipment and their facilities. I also like to thank Dr. Keith, my mentor, Dr. Mary Keithley, and Jen Walmart for their support and encouragement. These are my sources, and thanks for listening.